Hello everyone, welcome to this talk. I'm Zhimeng. In this video, I will be introducing the paper Streaming Nonlinear Bayesian Tensor Decomposition, which is done with my colleagues Zheng Wang and Shandian at University of Utah. Okay, let's get started. A tensor is just a high-dimensional array. Each dimension of it could represent a certain set of entities, such as customer, product, and brand. Tensor decomposition is a fundamental framework for multi-way data analysis and has applications in many areas like online shopping, social network, and traffic prediction. Many successful TD algorithms have been proposed and proved to work very well, and most of them operate on collections of static data and perform batch processing, or say training, for multiple epochs. However, in many applications, data are generated dynamically and incrementally. It would be a natural way for our algorithms to process data in this streaming manner. Besides, there are cases where we are not allowed to revisit data once processed, say due to privacy reasons, or the data size is so huge that it is impossible to reuse them multiple times. Therefore, we need algorithms that could handle data in this streaming setting, which is the focus of our method. There are several existing approaches that could handle streaming data. One powerful framework is streaming variational Bayes, short as SVB. SVB continuously integrates the current posterior with incoming data to obtain the updated posterior in a variational approximation framework. A successful application of SVB is POST, a multilinear streaming tensor decomposition algorithm. Despite its power, SVB is only suitable for multilinear methods. For nonlinear methods like sparse variational Gaussian process, the variation posteriors for embeddings and city inputs will be coupled in a complex kernel function, and the elbow is not analytical and we do not have any closed form update, and we have to resort to stochastic gradient descent to optimize the elbow. STD is extremely useful in traditional static setting, but not so in streaming. Due to its unstableness and the hardness to diagnose the convergence in streaming setting, STD often fails to provide reliable, high-quality posterior updates for every incoming batch of data, which in turn will affect the updates for the subsequent data. To address these issues, we propose a novel Bayesian nonlinear tensor decomposition model utilizing approximation of Gaussian process. Our model has the same nonlinear function with high learning capability as in other Gaussian process models, but the log drive probability is free of complex kernel and matrix operations, and therefore the posterior inference is much easier. On top of this model, we then develop a one-shot update scheme for streaming posterior inference that doesn't rely on STD. To construct our model, we first consider to approximate the kernel function using random Fourier features. Based on this approximation, we could build a spectral Gaussian process model with simplified data likelihood as a generalized linear model. Note that if we marginalize all the feature weights W and the random frequencies S, we will recover the joint multivariate Gaussian likelihood as conventional one. Because of this generalized linear structure in the likelihood, our joint probability will not include any complicated kernel computations and matrix operations, such as inverse and log determinant. Therefore, it is much simpler than the elbow of the variational sparse GP, and the posterior inference of embeddings will be easier and more convenient. Even though this model is still intractable to SVB, and we need to develop a new inference algorithm for this model. To do so, we seek to extend the classic assumed density filtering, ADF, which is a variant of expectation propagation framework. The shortage of standard ADF is that it could only process one data point at a time, which is quite inefficient, and it is sometimes unstable due to the existence of outlier data points. Thus, we propose a one-shot update scheme that uses a single factor to approximate the product of a likelihood of all data points in one streaming batch. Once we obtain this combining factor, the new posterior could be easily obtained by moment matching as in standard idea. Now the big problem is how do we obtain this combining factor? The key technique we use here is the conditional moment matching. In moment matching, what we need to do is essentially to estimate the mean and variance of a parameter under the blending distribution. Of course, the exact mean and variance by taking expression over blending distribution is intractable, but we could try to approximate them. In conditional moment matching, we split the parameters into two groups. One is the target parameter we aim to update, and the other is all other parameters. Then the expression over blending distribution could be done by taking two expressions. One is the marginal distribution of all other parameters, and the other is the conditional distribution of the target parameters given all others. The conditional moments are always feasible to compute in closed form, either analytically or approximately by Gaussian Hermite conjecture. The marginal expression is intractable most of the time, but we can apply the first-order Taylor expansion at the mean to compute it approximately. Once we obtain the mean and variance of the combining factor, updating the new posterior will be straightforward. Here is the outline of our inference operation. First, we initialize the posterior with some prior. Then, for each incoming batch of data, we use all the data points in this batch to construct a blending distribution and update the posterior in parallel with conditional moment matching. And we could continue this process until finished. Finally, we conduct the experiment to evaluate our models comparing with other competing methods using large-scale real-world datasets. The experiment shows that our model is first, more accurate with higher AUC and lower mean square error. Second, it is more robust with running curve much smoother than others. Finally, our model is more efficient as it takes less time to process one batch of data. To summarize, we have presented SNBTD, a streaming nonlinear Bayesian tensor decomposition method based on spectral GP model and a one-shot update scheme. Experiments on real-world applications have demonstrated the advantage of our model in prediction accuracy, robustness, and running efficiency. This will be the end of this video. Thanks so much for watching.